In a world that walks the line, there's a rare few who think outside the box together for the crew. To break the equations, not bound to any rule. Exposing to the world the universe's own view. It takes the talent of the craftsman, it takes the mind of the fool, to make the vision realize energy and matter in a duel. To a break, to a duel. The old man Bills was running through his head. Cheryl probably got it hiding under his bed. Penny up to Annie making power for days. Don't listen to a word that the straight no says. Mike building batteries that power a ship. Victor comes and talking math as the water spiral dip. Sean chucking plasma bolts a mile long. Sheila on the video making tones from the prongs. Bernie breaking matter, they said it couldn't be done. And to all the people in the chat, I know you're having fun. So it's time to spend your Saturday with the doping old man Bills.
Hello everybody and welcome. My name is Nathan, otherwise known as Old Man Bills. Joe, what's going on, brother?
It's Friday as usual. What's going on, everybody?
Oh man, good mood, Joe. Oh man, what's going on, guys? What's going on, Lightspeed, Dennis, man, hanging out today, brother. Oh man, get to look at some of Sean's cool stuff he's got going on. I sent you a couple of videos earlier. I didn't know if you had time to check them out.
Yeah, definitely check those out. Some definitely interesting stuff going on. He's at it again, playing with the configurations of everything, just seeing what the observations are, and it's pretty interesting because the direction that it's been going with it is kind of unique in a sense, because the RAV isn't forming, or at least it appears that it's not, in the way that we know it to work, and it's seeming like the way that he's doing it is actually leaning on, just maximizing the cathode reaction, and that's kind of what's interesting to me about it, is it's like, he's like isolating half of the reaction, and by doing that, it's giving the greater effect to the one side.
Yeah, I
That's
can see
sort
that.
of the way I'm seeing it.
Yeah, well, he puts it on the glass, and the glass becomes conductive, so it's like his little insulator. Once you saturate it, the energy flows, right? So now he uses that in order to make the RAV, and it's very small. He's making a very small RAV, so it looks like it's not there, but it is.
Yeah, it might, and you know what, and that was what was hard to tell, and that, because I wasn't able to talk to him about it, because you really can't see into the glass in that way to see, whether the RAV is fully formed or there. But in that context, that kind of makes sense, because if it's actually doing the work like we see, well, that means that the RAV is actually somewhat intermedium at that point. So it's actually, if you think about it, it's inside and passing through the glass at that point. Somewhat.
Shout out Dennis. He got one to actually appear. We'll have to take a look at that later on in the show. But yeah, you know what it kind of reminds me of, Joe? Like
What's
a
that?
hot ball on plastic, and it's spinning it, right? So it just seems like you take a metal ball, you get it hot, and you spin it on plastic, and it runs all over the place, makes its own lines.
Yep.
That's what it reminds me of, what it's doing.
Yeah, it's somewhat like that. But it's actually really interesting in a way, because it's like, it's reaching out in search the same way that it does when the RAV forms. So, if we go all the way back to the beginning, okay, before we really knew how to build the thing consistently and just almost instantly, right? We knew that when setting the material, it has this build-up process. And part of that build-up process is, the anode side is reaching and searching for those electrons to pull. into it to create the relationship. And in doing so, it formed tendrils, and those tendrils, it almost appears that they're reaching out randomly and unpredictably. But if you notice, they favor certain spots, and it moves in a pattern, right? So that seems to be what we're kind of observing here too. But if the RAV is forming, that's new because it's now creating the same types of motion processes, right? That it did in the first place to form, because it's following the same type of pattern.
Yeah, let's take a look at one real quick, Joe.
Yeah, let's do that.
So he's got the metal on it to make it the thing conductive. He's got water on the inside.
Yep.
Okay, and he's kind of jiggling a lot, but it's catching. But you can see at the end of it, it's like really white. Let's see if he can stop jiggling it. There it goes. It starts to form the pattern, and it just drives itself around.
Yeah, interesting how he did that. Okay, so you know what? When I looked at it initially, for whatever reason, I didn't see all the same things that I'm seeing now. But it looks like he's got the glass sphere, right? And then that has water in it. That keeps it kind of stable, but it looks like it's floating on the water. Is it floating on water, or is it being held up by a wire base?
He's got a wire base.
A wire base. Oh, okay. So I thought maybe it was floating in glass. Okay.
Oh, you know what? I see it now. Okay, hold on.
Floating water.
If you look over to the right, there's a wire that goes into the ball.
Yes.
And then it goes up onto the top, right over by the anode.
Yep.
And then comes back down out the other side.
Yep, that's what I was looking at just now. That's why I said, is it just dangling on a base? Okay, so that's what it is doing. Oh, that's interesting. I mean, so he's got water in there, but it's not
reaction.
But it's not touching. So the wire's not touching the water.
No.
Yeah. Okay.
So I don't know what the water's use in there. Maybe just the weight.
I mean, to weigh it down, yeah, probably. But I mean, truthfully, it would have been interesting to know if the result would have been different if the wire were rigged downward rather than upward, just so it contacts that water.
Well, I think the wire goes upward so that it can contact the anode is probably what his mindset was.
Well, I understand that, of course.
And I see the RAV at the very end of it. You
I
can see the
too.
ball.
Now, yep, in a freeze frame, I see it. Yep.
Okay. And then it just forms its own little pattern, goes where it wants.
Yep. That's what I was talking about. You see how it's doing the dance like that? It's that pattern that I was talking about initially. You see how it's the same as when it was reaching, but you don't see it as tendrils now. You just see it as motion of the sphere.
Uh-huh.
Yeah, that's pretty interesting.
Oh yeah, like I said, it's just it's carving it out is what it's doing. And he says it's called a Merlot set. Or no, Mandelbrot set.
Yeah, Mandelbrot set. I mean, loosely, I don't think that's wrong. A Mandelbrot set is just a very specific fractal pattern that occurs, but like all fractal patterns, well, not all, I shouldn't say, but most, when it works off of like primes and stuff, what ends up happening is it starts off small, and it'll gradually increase in its reach and its width, right? And then it'll reach a certain threshold where it will actually expand by orders of magnitude rapidly. And it'll do that until it then starts to come back down gradually and then collapse just as fast as it came about. And it's symmetrical, right? So what you end up seeing is it's like a line, a really big expanse, and then contracts, and then a line, and then it repeats that process over and over again. I do see that kind of patterning here. The only thing that I have to kind of wonder a little bit is how much of it is due to what he's doing right now in the video, versus just the natural.
I don't know what he's doing right now. Yeah,
See,
I think
he's moving it around is the thing.
well, yeah, he's trying to get to an empty space so that it can run its course.
Yeah, no, I got okay. I mean, that's it would be nice to see it on a fresh piece just to see what it does.
Well, let me see if I got another video.
Yeah, well, there were other videos. I know that.
Let me see if this is the same one. He's got that stick in there. Maybe that's the same one. Okay, hold on. Maybe I downloaded it twice. Yeah, I did. Okay.
I mean, I think I know what he's going for here. I think he's trying to get lightning out of the equation. If I had to guess.
I wouldn't get lightning out of that. I wouldn't even.
Yeah, I'm just looking at the configuration though, and that's kind of what it feels like.
I think he got set on how these things build out and the look of them. Here we go. It's a different video. And I think that's what he's going for. Hey, you just about write your name in this thing.
Yeah.
Got to give him a different stick, though.
Yeah. Well, that, you know, like I wish the video was just on a clean surface from the get-go, you know, and not poked around once it gets going, because again, it's hard to judge actually what patterning it is or isn't doing if the, you know.
Okay, real quick, Joe, my mistake. Sean says Julia set, not Mandelbrot.
Oh, Julia set. Okay, well, yeah, now that actually does make sense too, and it's similar because they're both fractal patterns.
Yeah, I think he's just trying to get the open area so we can get the design. That's what it looks like. Water was to stabilize. He sent me another video. I don't think we've gotten there yet, Sean. Yeah, for like fractal, you guys said the same thing. We're good.
It is. I mean, Julia sets are the patterning is different on them because they're spiralitic, which would make sense for a RAV since it's rotational, especially, right? So, but they still follow the same expansion contraction patterns as a Mandelbrot set.
Shout out Traveling Fools, man, hanging out with us, looking at some cool stuff.
Okay, right on.
Yeah, take a look at that, Joe. I love the fact that he put the different light in there so that you can see it.
That is cool.
Yeah, you can see the patterns and stuff really well.
Yeah, you definitely can. Here, in fact, freeze it real quick. Let me zoom in on that. So yeah, I mean, I could definitely see what Sean's saying about it being a Julia set, because you could see the rotational etching in it, which again isn't surprising because of what the RAV is in the first place. We know that it's rotational, you know, so that's a significant factor in it. But it does build out in that sort of way where it starts off centric, it expands outward. You know, it has specific points that grow out further than you know, others on the outer diameters, and then when it starts to move out, it thins out before starting to repeat again. So I mean, I think that that's a great observation that he made. I think that that's definitely true.
Very cool. Let's look at this in another color. Yeah, that's just neat. All right, Sean, you definitely got me as a fan with the different colors. I'll tell you that right now.
Yes, it definitely scratches monkey brain very, very hard. Yeah, gives it a tickle.
Look at that. I mean, it's just awesome.
Yeah. Well, I mean, not to mention with different colors coming through it, you know, gives a greater chance to make different observations. You know, because the certain wavelength that's coming out the LED, you know, it could very well have pick up on something that another color didn't.
Absolutely.
Mhm.
Okay, so he's got another video here. Hold on.
There it's on clean.
Oh wow, okay. This went out of control. There it goes. Well, look at where the cathode is. It's
Yeah.
right in the center, and there's an open bottom to it,
Uh-huh.
which means he has to have that glass saturated for energy.
Uh-huh. Right, yeah, it's past its insulative threshold.
Yeah, it's just wild how that gets on there, and he gets that RAV right away again.
Mm-hmm. Now, what we just saw there and what's actually happening right here, right now, is actually very interesting, and probably more interesting than it looks. Because since it's basically pulling the cathode energy right through the insulator.
Mm-hmm. Absolutely.
That actually lends itself to what I was saying about when I said you should get with Bernie and you should put the one in one jar with a wire to a clean jar of water,
Mm-hmm.
right, and then run it on that water, because I think that you would pull material in that case right into the jar, and this runs the same concept. Okay, the idea, and in fact, it'd be easier to do what I just said than it is to do this. The idea here is that it's pulling electrons through the insulator.
Yeah,
to form the RAV. Yeah. Yeah.
it's neat. I'll hit mute and play it
I mean,
again.
also the hollow of the glass, it's probably accumulating a large negative energy bias inside of that in general too. So you have a huge amount of ionized gas probably that's inside of the sphere.
Yeah, what's cool is you see it go to the cathode. You see the purple inside, and then the purple at the end when he gets it set goes away.
Yep, it does.
Oh, he's hitting the corner of the glass with the cathode.
Yep, I see it. He's hitting two spots. He's hitting one side, but then it was conducting through the other too.
There he goes. He got it steadied down.
So I mean, I think this is a great example, Nathan, of inside of that sphere. When we talk about charge bias potentials, where there's a state of potential and there's just a charge bias, that's what's probably going on inside of the glass. You don't see any active electromagnetism or plasma reaction, but that doesn't mean that it's not saturated, with a charge bias.
Hey, Joe, one thing to look at, and we'll have to look at this later. Look right in the center. There's 4 little dots. I don't know if you could see them. There's the hole in the glass, and then if you look just left of that, you'll see 4 little dots appear right there. Let me see if I can't play it.
I see the dots.
Okay, so
there they are.
Yeah, I want to maybe. I'll take this thing and I'll slow it down and zoom.
I'm trying to understand if that's a reflection of what's going on at the top, because I think it is, or a reflection of what's going on behind.
That's what I want to see, because they're moving. They're going up and down. I can see them right now.
Yeah, they are. Right. Yeah. No, they're not static. So that's not an environmental reflection. That's there.
Okay, but there's a line that goes to one of them.
Hold on. So let's look at the top and the bottom at the same time. We can.
Right there.
Okay.
What is it? If you go all the way to the left, the one to the right of that, it has a line straight down from the where it's coming from. I'm looking to see if it's magnifying glassing it. You know what I mean?
Well, I think this might not be correct, but I feel like there's something to what I'm saying. I have a hunch that those etchings that the RAV is making on that glass, that if you were to shine a laser through it and you were to project that laser onto like a piece of paper or something like that, there's a
Mhm.
possibility that it may be holographic in nature.
Oh, yeah.
Like, it's possible that it's literally, that's just carving information, about itself into, into the surface. And it's possible that light might actually reveal that, I think.
Yeah, we're gonna have to research that a little bit more because I want to see when they show up and slow it down and then zoom it in. And I just want to see because I can see the little line above it right now, and it'll go away as soon as I hit play.
Yeah,
And usually when we get that, see, it looks like there's an energy line. Can you see it? It's like
absolutely can.
very, very
Absolutely.
faint. But it looks like it's an energy line coming into contact with it. So I
I
can't tell
wonder
if
about
it's,
those dots, man. That's interesting.
yeah, that's what I'm saying. I mean, there's something there, and I don't know what to call it, but I can see it.
Well, they look suspended at different distances.
Hmm.
Like, is one on the outside or whatever, the closer side to the camera, and one's on the further side of the camera, and then the one's underneath? They're clearly moving around.
Oh
There's
yeah.
also something on the surface of the cathode that's in front of them. If you see that,
Okay. Let me see.
another dot looks like it's on the surface of the cathode. Oh,
Yeah,
Nathan, it's on this outside of it too. Look at the outside. There's two light dots.
I see those.
You see those two, right?
They disappeared.
So does it have to do with the light of the RAV shining through the etchings and causing a refraction and then causing, like I said, like some form of like hologram?
Absolutely, Sean. Anytime you want, buddy. Give me a second. Sean asked to join, so I'm going to send him a.
Oh, awesome.
He'll clear it right up for us. There you go, Sean. I sent it for you, bud. Yeah, so many little extra things. It always goes on in his experiment. You know what I mean?
Mhm. Yeah, that's pretty cool stuff.
Yeah. Somebody tried to tell me, remember that one that Sean was spinning and you can see the thing going around like this? He goes, some guy told me his flashlight did that.
Hmm.
And I'm like, yeah, dude, I don't have any kind of flashlight that would ever do that, bud. You know what I mean? Not a chance. Give me a second. Sean popped in here. Let me remove some stuff. Where are you, Sean? Oh, it says device not connected. Something's going on with your camera there, Sean. Try to go out and come back in. All right, there you go. It just popped out. Yeah, I always have to look at the stuff in slow motion to find out what's going on.
Yeah, still frame, slow motion. You almost have to take it one little tiny piece at a time because you see some interesting stuff playing it through. but you never really get the full picture until you actually take it almost frame by frame.
Yeah, never. So here we go. He's got a couple in a cylinder, Joe. So he's getting the same effect. But I don't see any little lights showing up in this one. Oh, I take that back. Look directly behind it. There's like a reflection.
Yep. Let's see that. Well,
Okay,
first of all, just the way that the light is like, it's kind of like refracting through there. Do you see that? How it's like a dish?
Mm-hmm.
That's unusual in itself because
Hey,
that
guys.
doesn't exactly match the geometries of a regular cylinder.
Yeah. Sean, you there? Well,
No,
no, I don't
we
hear
see
him.
the box, but we don't see our Sean. Where'd
Yeah.
he go?
Well, no Sean yet.
1, 2, 3.
Oh, we
I
hear
hear
you.
him.
Ah,
He's just left again. All right.
all right.
Get him back in a minute.
But yeah, I don't know what's doing with that because that's interesting. And then if you look at the end of it, which is completely opposite the RAV itself, right?
Uh-huh.
That's where the reflection of the RAV appears to be is bottom right corner.
Hey, guys.
But you could like see it bending.
Can you guys hear me?
Yeah,
We can
Sean,
hear
we can
you.
hear you.
Sorry about that. My camera's going to take a little bit, but I'm feeling a bit better health-wise, and this is such an awesome occasion for me when I can get your two big brains on looking at my experiments instead of me staring at them alone. So so you so what you're seeing here is a glass straw. You can buy them. I don't know if you heard of glass straws. Um, so it's about, I would say, 8 to about a centimeter in diameter. The glass is pretty thick. And as far as how the RAV operates, it's probably what you would call a clean RAV, very clean. If I look under like a welding glass, it's about as spherical as you can get. The pattern that is occurring on there is not etching; it's melting, and then I think I sent it to you, Nathan, or I can send you another one. But when you put those markings under a microscope, it clearly looks like Julia sets. It has that Julia set look. Though the technical name is from fluid dynamics, it's called the Laplacian interfacial instability. So that's the technical name. And it just talks about fluid dynamics because when you do a zoom in on this, you'll actually see bubbles, and it sort of has that water kind of feel to it. So that's what's going on right here. You'll notice that sometimes I'll have a wire down at the bottom, which you can barely see here. But honestly, I never need a cathode wire. I've tossed out the wires altogether. If I just train the glass like I showed you with that sphere, where I kind of rolled it around until the cathode disappeared, what's happening is exactly what you guys said earlier. It gets saturated to a point where it reaches that temperature that it frees the electrons, that is similar to copper. And so therefore then you can now just operate the RAV on top of the glass, and depending on the thickness depends on how good of the well, I just named this today because I was pulling my hair out. I'm just calling these no, never mind. It's the next phenomenon I'm going to share with you guys. But this is what the Julia set, when I say Julia set, this is what I mean. So if you can zoom in to kind of like these little snail trails things, if you could zoom it in with your mouse wheel.
It won't zoom in. Let me cut a picture real quick and then I'll do it.
Okay.
Hey Nathan, I think an old trick back in the day, if you wanted to zoom on one of those things, is like you hold control and then you like roll your mouse wheel, you know, or something like that, and then it zooms in.
Oh
I'll give
yeah.
it a try. Hold on.
Okay, I can look for his. Oh
No, no,
wait,
no. Oh, you learned something new.
nice.
No, but it's not going to give me the zoom
It
I
won't
want.
zoom in though. It'll only zoom out.
No, it zoomed in and out, but it wouldn't go any bigger.
That's okay.
Just give me a
So
second.
when you look at the
I'll do
maze
this
of
thing.
bubbles, they go from the larger bubbles to the smaller bubbles, which is interesting. It's not the other way around. So if you were to ice skate, like on a path, oh, that's brilliant. Nice.
Yeah, very cool.
There you go. So there's a couple cool things here. It'll go. So those basically, like, think of it walls in a maze, and in the walls you have the larger bubbles inside the path versus the smaller bubbles outside the path. And then when I've really drilled into some of the in-between parts, you actually will get a whole nother labyrinth. So that's kind of why it's interesting to relate it to a fractal, even though no fractal math is associated with this. This is just fluid dynamics. It just happens to do this because nature does this. See that white part there? That dense part. So that's another part of this phenomenon. There's three parts. This is the second part. Those are all just thousands of little glass vortexes. I think I have a better. I'll send you a little bit better photo where you can see them. But they're little glass vortexes, and what happens is that the RAV will kind of run and create a little maze, but every once in a while it'll shoot in and do some donuts in the middle of the maze. Then it'll go jump back out again, make the maze bigger. It'll shoot back in and do donuts. And so that denser part there where there's a little glass vortexes, that's where the RAV is doing donuts. Now, if I leave that RAV in the center, you enter a third type of structure, and that structure actually turns color. It's like a magenta red, and the vortexes are larger. They look like little glass tornadoes, and it's strange that it's red because there's no color in this glass. There's no soot. There's no burning. But when we go through these photos, you'll see it almost looks like a scrambled egg. And but those are the three phenomenon here. This is on tubing, like that straw that I showed you earlier. So yeah, that's it. What do you guys think?
Yeah, I was gonna say let's talk about this real quick because I think I have a couple of these principles on lock, and that would probably adequately describe a lot of the behaviors that are occurring with the RAV, you know, when it's forming these things. So let's talk about the tubes first. You know, the more tubular structures, right?
The path.
So when the RAV is in motion, you know, and it's melting the glass, it starts to you know, it's not resistance, that's not the right word exactly, but it has one of a couple of things that can happen, right? It's either going to sit there and start to turn, okay, and start to catch an edge and then work itself out, okay, because if it didn't work itself out to actually form the tubes like that, then it would shear. The same as a waveform shear, the same as anything shearing. Once you twist it too much, right? Well, then you just end up back where you came from because you're dealing on a plane. You got to remember this is you know, a RAV, you know, which is we're seeing in 3D. It's probably more than 3D, and it's having this effect on a 2D plane of a 3D lattice. You have to realize how dimensionally you know, relative it is, right? So, but its movement vectoring is on the plane of the glass. So now under the normal circumstance when it's not energetic enough, okay, it's gonna resist shearing, okay, because it takes a lot to make that turn. That last bit of the turn to shear, okay, is the greatest amount of energy. That's where the threshold exists. So it'll, instead of doing that, it'll kick out and then start it again. And that's how you get that repeating tubular pattern. Okay. Now, when you see these bubbles form, okay, in these clusters, you can still see the tubule motion,
Yeah.
okay, within it. However, you see that in that case, it did shear. So it had enough energy, okay, to shear and then start just basically working that one area.
Yeah.
And once that occurred, there was enough energy transfer, okay, because we know that that's how this works, is through energy transfer, okay, through the intermedium of the glass, through a phase shift, okay, of the material, okay, because then there's a phase shift of the material from a solid to a liquid, okay, there's
Yeah.
able to be something transient through it
Yeah.
beyond just through the lattice structure. So it takes it from a microscopic effect at that point to a macroscopic effect. And
Yeah.
in essence, what it's doing is no different than what the bubbler in the thunderstorm generator would do. Okay, which is taking the transient gases, bring them into a different medium, having that then form a bubble. And then in this case, because it's glass, it's solidifying, and it's solidifying probably with a plasmoid inside, which is super interesting when you get down to it, right?
Uh,
Yeah.
yeah, that
Sean,
sounds familiar with what I'm writing or researching for this. The middle part of those like little tornadoes, the process is the called advective aggregate instability. That's the fluid processes, and then the paths, which looks like snail trails or tubes. That's the Laplacian interfacial instability. Um, the what you have up here, Nathan,
hmm
is a quaternion. It's the 4D shape of the Julia set.
Mhm.
And so what I wanted to show you is those rods of glass that I sent you, Nathan.
hmm
So when you saw just now the flat surface, those are 3D Julia sets. When we go to the glass rods that you're going to share here in a minute, you're going to think of the 4D Julia sets. So here are the different sizes of rods that I use. They're nothing special, like I said. They're crafting straws, they're drinking straws. Amazon, you get 20 of them for like $5. The thin tube on the left, you buy 100 of those for $6. It's like a lab supply. It's a borosilicate glass. It's like a 1.9 millimeter diameter. They usually come about 5 to 10 centimeters long. So when you're looking at the flatter fractal-like shapes that we just saw, they're on the thicker tubes. The thinner tube, oh, that's perfect, Nathan. If you can go back to that, it's perfect.
Sorry. Give me a second. That one?
There we go. It's perfect. So on the bottom, you have the rod, the glass tube. Sorry, it's about 1.8 millimeters in diameter, and it's just a perfect tube of glass. But as the RAV works its way through the tube, it actually reshapes the into a solid glass rod. And in the reshaping of this, what you're getting here is that quaternion 4D shape.
Yeah, you're
And
getting that channel.
these are all basically vortexes in this glass here. And so that's the most fascinating thing right now, because when you dig into the structure of what this looks like, there's some very um, you won't see it anywhere kind of objects. I'll I'll send you one real quick here, Nathan. Wait, here's an example, not the best, but what I had AI do is I said, AI, just put lines everywhere you see the shading. So there's no doctoring of the photo. There's only just putting lines instead of the blending that you just saw earlier in the rod. I call these vortex glass rods because I don't want to call them glass sticks and rods and everything else. So vortex glass rod. So this is what they look like. This is a camera shot. And then if you go back to the other one, then you're getting the AI drawn out the structures that you see inside.
That's actually a good way to do it too, and it does appear fairly accurate. And one thing that's important to point out here is that what it's doing to the glass here, okay, is more or less the same effect, just that you're doing it a little differently when you do the self-nucleating cathode. Because that's what it's doing, is it's nucleating these areas.
Yeah, I think that's a good way to put it. If Nate can show the video, the way I nucleate it is I have the plasma go backwards. It's glass. This is not liquid. Everything you're seeing is glass. But if you go to that one, Nathan, where the plasma is running from the top to the bottom, and you see, there you go. Okay, so when it's done, that's what it looks like. That's before the microscope. That tube is turned into this after the RAV runs through it and melts it all and twists it up.
So that's important to see, Sean, because in this you could see the differences in the diameter, right?
Exactly.
And it's those differences in the diameter that is the repeating pattern that it's causing. That's directly related to all sorts of things to do with it.
Yes.
Mostly frequency related. If you take a sine wave, okay, and then you turn the sine wave into a 3D object, by adding helicity and then just creating walls, that's what you see. Is it's kind of like an hourglass, like a repeating hourglass shape.
Yeah.
Like a complete, where it's inverted. You know what I mean?
Yeah.
It's always getting bigger and smaller.
Yeah, that describes the shapes definitely going in it. Nathan, could you go back to the first one where I'm comparing with my hand, picking up the rod and then picking up the vortex glass
Give me 1
rod?
second. Yeah. Let me see where I found it.
There it is. Oh, stop there. Stop there. Okay, so this is the RAV making the vortex glass rod. So notice how the RAV is starting from the top and it's working its way down. This is way, way against plasma physics. Plasma physics always goes up. So this totally makes, it's very strange what it's doing here. So what's happening is you'll see the RAV at the bottom of the purple streamer, and it's going down and it's rearranging the clean glass tube below it. Now this is an interesting one because the glass broke off at the bottom. So you can see that the cathode runs to an air gap, it's an orange spark, and then it hits the rod again, and then it goes up to the RAV to form the circuit. Do you see that?
All right. Before I lose this thought, Sean, and I'm sorry to interrupt.
No.
But it's like you said that this is against common plasma physics, right? But it is, except for the fact that this isn't the stuff that plasma physics has been playing with, and the reason that it does this is, I could explain it. There's again always been an offset bias of the energy density levels between the cathode and the anode, right? The energy bias is more anodic. The anode's going to be able to pull, and meet, the state of interaction where the RAV is going to form in the non-equilibrium, closer to the anode side initially. So the conditions are set closer to the anode side. The anode is therefore on the top in this case, right?
Right.
Then, as it's working its way down, as we said, it's nucleating that And, you know, because it's an insulator, right, the anode just can't simply penetrate it. It needs to be conditioned in
Mhm.
order for it to come any closer to the cathode. However, it does always want to get closer to the cathode. So therefore it works its way down. You know, and that's why it doesn't stay in any one spot, and it's working itself closer to the cathode. The up and down aspect of it is actually interesting because I believe it's only relative to the configuration that you place the anode and the cathode in. So if you were to flip the configuration upside down, it would then work down to up.
Yeah, it wouldn't work at all.
It wouldn't work at all, or it would work down to up. So I think it would work down to up.
You can't. So this is what's weird. I see what you're saying, and that's totally logical. That you're going to see the anode, it's going to bombard the cathode with ions, and its ions have more power, so that's going to create the heat. I mean, that's totally makes sense. I guess I was just speaking to whenever you have plasma or electricity in the air, it tends to go up because hot air rises. And so, like, for example, if you see a Jacob's ladder, it ionizes the air, and then the electricity rises because, of course, warm air is lighter than ambient air. So that's kind of what I was meaning behind that. But I totally see what you're saying. I totally agree with what you're saying because, yeah, the anode is seeking the cathode, and
Right. The relationship is the pull. You
right.
know, right now there's an indirect feed. Right. The whole nature of how the chase event occurs in RAV formation
Hmm.
has to do with it attempting to complete a semblance of a circuit. But that's not how it's going, you know, in this case. Like because there's an offset bias of the energy, you know, it would only create it under the circumstances that it was allowed to fully penetrate and actually contact the cathode itself. Then under the circumstances of like a wire cathode, that cathode would self-nucleate and then contain the RAV, and that would be enough insulative property to hold it off the rest of the cathode. If you had a very large mass or something that you know wouldn't be easily defeated, so to speak, by the anodic energy and the RAV itself, right? At that point, it wouldn't go any further, right? So it wouldn't self-nucleate or fall through it. It would stop there. But at that point, it would complete a circuit, and then the RAV would actually collapse because the exchange is no longer the the exchange is no longer asymmetric. It's then just allowed to happen with ambient resistance.
Hmm.
Okay, real
And
quick,
back to
guys.
just before I
Shot.
forget, sorry, you can't change the position. You can't go sideways, you can't go upside down. If you guys saw me rolling around the glass sphere and how I was kind of training the RAV to go where I wanted it, and then boom, the cathode disappeared. It's that kind. There's gravity involved with this, and there is the ambient air forces that if you try something other than this right here exactly, you're not going to get this result. And I haven't fully figured that out, but
Hmm. Okay.
this is stuck in this geometry for now, at least.
All right, guys,
I'd
real
love to
quick.
explore that
Hold on.
some more, you know, like
I want to shout out Gutter's Pub for becoming a member of the show, guys.
right on.
Thank you very much,
Welcome
Gutters.
aboard, Gutters.
Hold on, Gigi. Thank you.
Welcome aboard, Gutters. Thank you for joining.
Guys, by the way, you guys got to remember how this is being built in energy. You have an AC flyback, which is bipolar in nature. So it'll set itself. Normally, when they do plasma physics, they have it an anode cathode set based on bias. So it'll be a magnetic bottom and then a high voltage top, which means it'll rise up always because the heat and the way that it melts. In this configuration, you have a bipolar setup, so it's bouncing back and forth between it.
Hmm. Yeah. I can see that. It's worth noting too that plasma does not create these geometries. Try to look it up. It'll only tell you, AI, the internet, that only Lichtenberg shapes can be created by plasma on materials. So when I was creating these Julia set, but both the quaternion 4D like you see here in the rod, and then the 3D earlier, I can't find a place that does it. They say it, you can't do it. It literally says, AI says you cannot do that. And
Well,
that's
hold on, Sean, I could explain that too. All right. The reason that they're saying that the plasma can only form Lichtenberg, okay, is because they're not taking into account that the plasma is in a coherent and organized and rotational form. Generally speaking, the plasma is either in a diffuse and unorganized state, right, or it's in that searching arc state that we generally experience, right? Well, we know that the searching arc state forms Lichtenberg patterns
yeah.
because it that is exactly what it does. It's literally sitting there putting the tendrils out, feeling and pulling out into these patterns, looking for the electron pull and the electron connection. And it does that and does that until the connection is made, and that's why they draw toward each other through the materials in that circumstance. But that's not organized plasma. So that's the point. If you were to put something, if you were to, look at etching patterns that occur in organized plasma states, it's always consistent with this because it's always spherical in its nature. Um, uh, Anything to do with plasmoids is going to form different, more complex, structures.
I can't find it, but thank you for that.
Well, it's the whole point of the RAV, isn't it?
Exactly.
It's the reason you're getting what you're getting. Otherwise, it'd
Exactly.
just be purple plasma, going onto the glass, which would be horrifying compared to what you're getting here. It wouldn't really work all that well. So
Right. Yeah.
you
I
have to
don't,
form the RAV.
yeah, I'm just comparing it to what plasma shapes that give to these organized structures. I can't find it that makes these structures, I guess.
Well, you got to remember too. You're the cutting edge of science there, and Sean. It's going to be you're going to write the story on this one because they haven't seen it because they don't make these.
Yeah, nobody's doing it like this. Nobody's trying them.
Nobody.
I appreciate it. Thank
Now,
you.
one thing that's also interesting about this, Sean, is that you could see that the anode and the arc itself, okay, it has no real interest, okay, in actually channeling itself, as a carrier through the structured glass, okay, even if it's hot. So after it's structured, and what that's telling me is that the glass saturation is purely cathodic, and that where the RAV is forming is the front line of the interaction point.
Yeah.
What's that interesting is that means that the electron flow and the saturation levels that are present in the rod, okay, through the cathode, okay, that line is actually getting pushed further and further down as the RAV moves down. So,
Yeah. And
that's sort of interesting.
yeah, you're 100% right. The glass tube becomes the cathode, and that's amazing to me. I just sent you some photos, Nathan, of the 4D quaternions that I'd love to get you and Joe's take on because I just sent them. So the 4D, yeah, there we go. These are the shapes that are drawn out by the 4D Julia sets. And what's interesting is that we'll see all of these. If you go back to the photos I took, you'll see all of these structures. And again, I'm not saying it's a fractal, but there's a strong correlation.
Well, there
You know,
is
like,
something interesting that you'd be able to see. Um, and it's depending on, again, it's depending on the light and also how far into it you could see. But,
Yeah,
with these Julia sets and the fact that they're 4D, you got to remember that there'll be that structure, but that structure will actually be repeating around itself in 3 dimensions. So it'll be that pattern, but then that pattern all around that, and then that pattern all around that. So you
right.
kind of got to see in to see that structure build out. The funny thing is that it builds one overall structure, but then you have all these substructures inside that are independent and part of that same
Up there.
thing
Yeah,
at the same time, you know?
yeah, exactly. Exactly. That's the beauty of the glass, is that we can actually peer into them, and AI peers into it better. But now that you saw those colorful Quaternion Julia 40 Julia sets, you now come back to here and you're going, oh man, I can see almost every type of shape in here.
oh yeah, absolutely. I can see it.
Sean, I have an important question. After
Sure.
you have a rod structured like this, right? It's cooled, solidified, the whole 9 yards.
Hmm.
Have you, other than look at it with a microscope and play with the images, have you done any further testing on those specimens, themselves? Do they have any unique properties at all? The way that they're structured? Do they? Have you tried to form the same reaction, through a rod that's already been worked, or
Um,
anything like that?
well, that's an interesting question. So what I've done is I've run laser through it. Um,
Mm.
I have, what else? I've created it with two different glasses of borosilicate and the soda lime. The soda lime were so brittle I couldn't get a clean picture. So the soda lime has its own kind of flavor. I was kind of hoping maybe a black light or a strong, powerful light or a laser would have some kind of effect. I didn't see anything. I zapped it with my handheld Tesla coil, not the one that I re-engineered from the Chinese torture device that you guys have. I actually bought, Amazon finally has a handheld Tesla coil for 45 bucks. It's pretty cool because it's pretty powerful, but it won't hurt you. And I didn't see, I was hoping to see something. Maybe there were gas pockets in there, and if I brought high voltage Tesla coil energy, it would, glow or something. I've also tried it with the bubbles, and it, I'm not seeing anything really different yet with just laser and black light and high voltage AC or high voltage DC yet. But I haven't tried doing one twice. That's a good idea, actually. I like that.
Well, yeah, I mean, there's multiple different things that come to mind. The laser is something I mentioned before, and that's a great idea in my opinion. Um, Another thing you could do though is you could cut wafers out of it, and then that way you could see right down the central axis of it, which will
Hmm.
give you a whole nother perspective, of what those structures look like, which I think is kind of a critical thing. And you're going to want to cut a bunch of those wafers and take a look, and then you want to shine a light through those wafers as well and see what comes of that. So
Yeah.
on the two-dimensional ones, though, the ones that you did in the glass, sphere, um, something about it, just like I said earlier, it just makes it seem like if you were to shine a laser through that,
Hmm.
that there may be some type of holographic uh, component to it.
Yeah.
I actually think that may be the case.
I have three different color lasers: green, blue, and red. I I shoot them through every time. to see what kind of design I get on the wall. It's kind of a hokey setup. It's not really stable and consistent, because I think that would give a more accurate result. So I'm glad you brought that up. I'll be a little bit more standard, and then send you guys I'll take some pictures of what I see.
Right. Well, now uh, follow me here. If the RAV itself, okay, is forming downward, all right, and it's working itself down at a certain rate,
Mm-hmm.
okay, that means that at the point of contact, it may well be locking in some form of information at
Yeah.
every layer that it contacts.
Yeah.
Now, if it's holographic type information, what's interesting is that any one piece, okay, should show you the whole. Okay, so if you were to just get a small fragment, okay, and shine it through, the way that it traveled, right?
Mm-hmm.
Then you should be able to get the information out. If you go parallel to the way that it was written, if you want to think about it that way,
Mm-hmm.
you may be getting multiple layers of that record. Okay, so you might not see the entire thing that way. But if you shine it through the other way, you should actually see it repeat itself as many times as whatever, like it should. And it should actually probably be 3D. It's just a theory. I don't know that it's going to work, but I think it's worth exploring.
I think of no, some good ideas. Nathan, can you go back to where it has the oh boy, my brain. It's the microscope picture of the glass rod that had AI fill the lines in. Could you go back to that?
I'll go back to that. You want to explain the RAV real quick right here?
So I'm not 100%. So I'll have to leave this slide for now, Nathan.
Oh, okay. Yeah, I'll take care of it, Sean.
Appreciate it.
Give me
Yeah,
1 second.
I'm having a rough time.
Not a problem. There you go. Is that the one?
Yes. So Joe, when you say that there could be some repetitive kind of structures, are you seeing some of that here in this? It's just a fascinating idea.
There's absolutely repetitive, and it's so easily identifiable. So you have the bulbous structures that are, running along the edge, and there's 3 lines of them present in this, which makes sense because you're seeing half the story, and 6 spheres around the round surface, is what fits. So there's probably six spheres that go around it. You could see the motion of those spheres are correlated with any deviation of the straightness of the walls, right?
Right.
And then you see, hold on 1 second, let me take a close look.
I don't mean to put you on the spot.
No, you're not. I love doing this stuff. It's this is my forte, so to speak. And
okay.
I wish I had seen this stuff though, because then I'd have it really broken down. But okay, so let's look at a couple different things that are going on. So first we see those 2 parallel wavy lines. Okay, sort of middle right. Okay. And then there's another one next to it and another one next to it. Those themselves are repeating. And that actually is a sign in that case of turbulence. Okay, because if you notice the botryoids, the round spheres, right? They're not forming in those particular segments. Okay. So that area is void of that. Now, if you also look, that is an area of the thinnest diameter. So when you have this repeating pattern going on where it's thinning out and then thickening, the thinner spaces are going to be the periods of where it's actually hitting turbulence. And the reason that you know it's turbulence is because you don't have the subvortices coming off the central vortice. Now, if a rotation, if the rotational energy is cause of multiple spherical subsets of structuring, well, that's generally an eddy effect current. So you have side convection that's coming off of the main rotation.
Yeah.
Now I want to look at if there's any indication of rotation bias in any of these.
And just to add to that, this is motion frozen in glass. That just blows my mind.
It absolutely is.
This is what the RAV is doing inside that glass.
Okay. So it looks like if you look at the spheres at the bottom, okay, the one at the far left and the one in the more center left, okay, those appear to have a clockwise bias to them. Okay. Now, if you look at the one in the middle, okay, it appears from this perspective to actually be neutral. So that rotation is hold on, I'll tell you. It is counterclockwise, okay, but actually rotated 90 degrees. Okay, so that's that one, which makes sense with what I said as it being an eddy current. And now let's look at the top ones. In the top one, that is a complex pattern, boy. Hang on.
And this is not the most detailed one. There's even
okay, hold on. No. That's easy. I'm just looking at it the wrong way.
Okay.
Okay, so that bias is counterclockwise. And the way I could tell that is if you look at the bulge at the top center, and then you look at the spherical dark thing that looks like it has an eye on the right, you could see the bias as it actually turns slightly parabolic. And you know where it flows would be counterclockwise. So you have a clockwise on the bottom. And what did I say? A counterclockwise, except 90 degrees rotated in the center, and then a clockwise bias on the top.
Yeah, the book New Kind of Heaven, that was recommended by Ian. It's the premise of the book is that he researches plasma, and then at the end of the book he says that the middle of the book, plasma contains information. It contains information in forms like this, but he's using more the example of lightning going through glass. I'm sorry, through sand creating glass. And then he takes it even further, saying that actually plasma creates life. And so when I first saw this, I thought there has to be information here because the book says there should be information here. And then, not coincidentally, but amazingly, you could just confirm that, Joe. That there's information in here.
Now, what I want to do real quick, and this is a little not usually what I do, but I'm actually going to leave the stream for a moment. Okay, I screenshot this. Okay, I'm just going to draw really quick on my phone what I'm talking about so you could see it, and then I'll send it to Nathan so we can display it. It'll take a couple of minutes. Okay.
Sure.
So I think that's worth it because I want everybody to see exactly what I'm saying because it's significant that there is a repeating pattern that I'm identifying right off the bat. So that's significant. All right, I'll be right back. I'm going to listen along though.
Okay.
All right.
Yeah, sounds good. So
Hey,
hey,
Sean,
Nathan. Yeah, go, Nathan.
Oh, I was just gonna say, Dennis was excited to show us his RAV. You want to check it out real quick while
Oh,
we're
that's
talking?
awesome. Yeah, yeah, of course. Excited.
Oh, he's got a Nathan Rav. It's bright as heck.
Wow. Look at that. What kind of clay? The clay looks really porous. He's, oh, there you
Wow.
go. Oh,
It was super
there you
bright, wasn't
go.
it?
Yep, it's right there. That's
Wow.
awesome.
Yeah, look at
Is
that.
you said Dennis?
Oh, boom. There it hit.
The clay looks really porous.
Yeah, I don't know what kind of clay it is, Sean. He said there's
Yeah.
water in the pan. He's got 3 videos of it, so let's give
Oh,
him a
good.
shot.
Oh, that yeah, I can see. So
Oh,
you
he got it
see
in
it
slow
how it
motion.
do you see how it's kind of etching into it, like creating like a little pit?
Mhm.
That's when you use a very porous clay. Um, but porous clay will give you, look at that. Porous clay will give you some really big ravs. It's just always one, it's a stability issue. Two, it digs holes in your work. It doesn't leave a flat work. Look at that. Yep. Nice. That's not easy to do. Oh man.
Yeah, that was a real big one, wasn't
That
it?
was a beauty, yeah. This is
Look at
Dennis?
that. Yeah, it's Dennis.
Dennis, you're the man. Well done. That's great work.
So he's got a small one, and then all of a sudden, he hit the gas or something, and
Yeah.
it was like boom.
Yeah. And you can tell it's not a flash because it's how it's spherical. If it
Oh,
wasn't perfectly spherical, that would be a flash. This is not a flash. That's a RAV.
yeah, look at that, Sean. He goes from the outside that's a real yellow like you get to
Uh-huh.
the out of control like I get.
That's awesome. That is so cool. Yeah. What's his power supply?
I think he's using a Tesla coil, if I'm not mistaken.
I don't I don't think you can do it that white with a Tesla coil. I mean,
Oh
maybe
yeah,
the
you can.
bipolar. Maybe the
Um,
bipolar.
you can make any Tesla coil, a bipolar Tesla coil, if you know what you're doing. But he
Ah,
he uses AC, I think.
that's
He would go ahead.
no, I'm sorry. Yeah, I'm just saying it looks like concrete or something.
Yeah, it kind of does, doesn't it?
It'd work though. I mean, his RAVs look great. That's salt. Immediately know the color. Oh, he's gonna grow some crystals maybe. I'm sorry I interrupted you, Nathan.
No, go ahead, Sean. They're here to hear you, brother. We're good.
Appreciate it. Yeah, so you're basically seeing a piece of salt. He's got the cathode and the anode working together here, which makes it difficult to create a RAV. You kind of want to calm the cathode down to really focus on that big, round, juicy RAV. But it's pretty cool what he's doing because he's going to get both RAVs when it balances. Um, I wonder did he put any water on the salt? I don't see it. If you put some drops of water on that salt while it's running, the crystals will start growing. Just a couple of drops of water while the plasma's on.
Okay, so Dennis says no variac on it on this one. It's 12 volts, 10 amp power pack.
Okay, and then what's the high voltage source?
Excuse me, Dennis.
Flyback?
Are you running a flyback or are you running a Tesla coil? He usually does his experience with a Tesla coil. That's why I ask.
Oh,
And he has the ZVS.
yeah, it looks like a flyback to me. I mean, but you've gotten RAVs to form with the Tesla coil, which made me jealous because I can't do that yet. Fly back. There you go. Yeah.
There you go.
Yeah. Okay. Yep. Good. Nice. Very nice. Dennis, did you put any water on that piece of salt? And if not, get an eyedropper. Start dabbing it on it while the plasma's running. And then, boom, crystals will grow in like a minute.
You know, when you put it into AI, Sean, and ask him about those little crystal things, they
Uh-huh.
say that they take a very long time to grow. But every time I see your videos, they're like growing in seconds.
That's another thing that when I research with AI says that you do everything in the laboratory that they try to avoid. I use too high a voltage. I melt the glass tubes instead of running the glass tubes in a controlled environment and not melt them. I use them in ambient air where they always will put it in a vacuum chamber so they can control the pressure. I mean, basically a RAV breaks all the rules. And so when the rules are there, those crystals grow super slow. And most of the time they're microscopic. But you're right. I can watch them grow. You've seen them grow in like 30 seconds a minute.
Yeah. They're talking like hours or days.
Right. No, you're right about that. It's everything in the RAV laboratory is anti-laboratory practices.
I
It's
love
so
it.
true. It's
Oh,
hilarious. AI will tell me, hey, why are you melting the tube?
yeah.
Why are you putting water everywhere around 60,000 volts? Why is your voltage so high?
Yeah.
Why are
Well,
you
you
doing
know,
ambient air?
they got to learn something different, Sean.
Yeah,
That's kind of the thing here. That's why it's important to do all this stuff. This is why you can't use somebody else's work, by the way, when you want to describe plasma physics,
yeah,
because their conditions are completely opposite of yours. So
right,
they wouldn't even have a clue what you're doing or how to even get it started, let alone define what you're doing.
right. Do you remember the video of the glass ball at the start and how it
Mhm,
was rolling it around on the cathode pan?
mhm. I
Um,
remember that.
I, Nobody does that. Nobody rolls glass around until it becomes a conductor that allows you then to shape it. There's no, you can't find it anywhere. Glass doesn't conduct electricity other than to be destroyed. But you saw that in the video, how it
Oh,
just
yeah.
rolled across the pan.
That was one of the best parts. It's like out of control, and then you get it controlled again, and then perfect.
Right, exactly. And then it's because of my poor health. I'll just sit there and run RAV experiments next to my bed. Wait a minute,
Next to hold on. You're laying in your bed and you're making RAV experiments.
I'm rolling RAVs, trying to get rid of the cathode away, and it's true.
Oh, that's so awesome, dude. What are you
Uh,
doing this morning? Well, I got my coffee next to me in my bed, but my RAV is running right next to it. I love it, John.
Next to my bagel.
Oh, all right. Okay, let's. I'm gonna put up Joe's. Give me 1 second,
yeah,
Joe.
yeah, it was a little more complicated than I wanted to make it. And I spent time. But what I did was I marked where like the rotate, where it appears the point of rotation probably is, and then what it appears the direction is. And if you look at what it's doing, it's acting like eddy currents, how they roll off of each other.
Hmm.
Yeah, that's a really good way to put it. That's a real good way to shape it because I totally see it
Yep.
completely.
Yeah, that's exactly what it's doing, man. And then there's substructures even within it. And that's because it's fractal. So these have their own substructures too that are in a state of like semi coherence.
And
Um,
you're consistent exactly with that book, where he makes the case that there's so much energy in a small plasma created object that it could be DNA for life, like, or more than that. So you're just totally like verifying what I'm reading, Joe, in that regard.
well, I'm glad if anything it's consistent because I mean this is what I'm seeing at least, and it's I don't know, it's pretty out there. There's so much going on in this that you know you, you could do a whole entire study on the one photo, realistically. You know.
Yeah, I agree. I have probably 100 pages of research on this and the 3D Julia set phenomenon. Um, so the fluid forces that make these shapes on this glass here is called advective aggregate instability. Again, just another fluid dynamics, but that's what this aligns with from running
Well,
these photos and researching.
now I don't know what that is, to be honest with you, to have a critique as to whether or not this applies. You know, I'm sure if that's what you found, it does. But where my mind automatically goes is I don't believe, right, that people are generally structuring and creating a phase change, structuring glass or fluid in general, and then having it freeze frame solidify in its based on the electromagnetism of geometric forces of the field interactions. You see what I mean? Like, I don't think that that's
Yeah,
what
I
people
agree.
like. I don't think that that's something they do. So how relative anything could possibly be to that, I'm not certain. Like, you could see these types of hydrodynamic uh, dynamics, in play. Freeze frame, if you were able to, observe. But then when are you doing that again? Liquid state phase change with electromagnetism being the mechanism of the flow pattern. You see that's where I get a little crippled with. Is there a direct concept to do with this exactly like described? I don't know. I'm interested in looking into what it is you're saying that the closest thing you said is, because I just don't know enough about it. But it couldn't be based off of the same observations for the same reasons, because I doubt they did these particular types of experiments, you know?
Sure, sure. Yeah, it's just the processes that work in fluid, and what I was able to, in plain man's terms, for that advective aggregation instability, it just means that if you have something spinning, then when something is spinning, it's spinning in, then hardens, then it's going to be in the shape of the thing spinning. That's kind of the layman. So when you see these tornadoes or vortexes, well, the RAV is a vortex. So that's kind of the simplest definition of the big words that I learned for this process. And you're 100% right, Joe. No one's doing this. No one's not even close. It's completely absurd. When I try to get any comparison, I have like 6 research papers that are sort of close, and then as I read them, they're a million miles away.
Yeah, well, we could always help get that on track if need be. It's never all that far off, man. You always hit on the key points regardless. I'm still obsessively looking at this thing on my monitor, um,
Hey,
just because there's so much there.
The work of art.
hey, Sean, I got a question for you.
Sure.
Do you think the glass is at the point of saturation when the RAV is doing this?
I do. So when you say saturation, you're just basically saying that it can take it's at the point of heat where it has free electrons everywhere to do whatever you want with them. So yeah, the RAV reaches saturation definitely. When you look at the labyrinth sort of shapes, on the flatter shapes,
Hmm.
in the center of those, you're getting this action as well. The little tiny spinning twirly glass tornado shape objects. So when you look at this, it's just doing it what I believe is in the quaternion, which is the fourth dimension. Because when you pulled, I wanted to ask you that, Nathan, when you saw those colorful twists and turns, screenshots that I sent you, are you seeing those in these photos, microscopic photos?
In this right here, I don't
Yeah,
necessarily see the labyrinth. I see the thicker part where it's starting to swirl a whole lot more in this one, because this
yeah.
one is on the little piece of glass stick that you had, and the other one is on a flatter surface. So I'm getting more of the areas where it's concentrated tornadoes in it, is what I'm
Mhm.
seeing here.
I see.
I want to bring a couple of things to light here about an overall picture of things based on a handful of different experiments, and then let you guys be the judge as to what it means. Um, now, if you look in the patterns of how this is structuring, okay, it's structuring the way that nature demands. All right, and what you'll notice is that you see a lot of uh, shapes and patterns and configurations that are very consistent with how cells build out, okay, and how you know like organic and biological structures build out, like anatomy and such, right? And then I want you to think real quick back to like how it was patterning on the glass, and like structures like that resemble like GI tracts and things, like those are the patterns that those generally fit into. And when you look at how it builds out in like more Lichtenberg type patterns, you realize quickly that your nervous system builds out in, quite frankly, a similar way.
Hmm.
Now, I want to say two things that is the crazy part of it, right? Well, when you see Sean building the crystal structure, on the cathode side, and you see all the snowflakes, right, forming, and then you look at how they form, and you look at what they're doing when the energy is still on. Energy is still on, meaning there's plasma and ions and exchange going on in that circumstance to where they're forming. They move organically. They move like something that moves that's alive. It's very strange, but I've seen
Yeah.
it repeatedly. They have this motion to them that uh,
Yeah.
is not accidental. It's not force related or wind related or something. It's literally like a twitching sort of motion, like that would remind you very similarly of like a moving hand or something like that. It moves in that way. And I would propose that that's because you have um, the plasma in a direct relationship with the matter. In that case, um, and then you look at your body, right? And what we know about that. Well, we're mostly water. Well, what is water? Water is the energy trap. You get it? It
Mhm.
holds all the hydrogen from being able to return to the pure energy state. It traps that pure energy as matter, water.
Mhm.
Um, so when you start building matter structure, and then you add the element of water, well, the water is then able to trap plasma, in such a way, and energy, high energy potential. And if it's in relationship to that matter, the general matter, and then the water and the
Mhm.
plasma, then that could very well be the constituent of life.
It's it,
And you see it all structure out, and then this is exactly what you're left with.
yeah, you're drawing the same conclusions as this author. I did get a RAV to go in water. I sent it to you, Nathan, just because you mentioned it. Is that something that'd be interesting to talk about? Is the RAV that's in water?
Yeah, hang on. Did you just send it?
I sent it to you over this week, so maybe, and I send you a lot of stuff, Nathan. Sorry.
No, it's okay. You know what? Hang
I'll
on.
try to
I think I
find it.
see it, but I'm gonna show
Yeah, let's
everybody
talk about
this.
water.
Just
That's cool.
You can show the one where it's orange inside the tube.
yeah, I'll
Oh,
do that. I just want to show this one first because
this
I
is a
love this
fail.
picture.
This is a
This is
big
just
failure.
I love plasma. You know me. So when you send me something like this, I always get excited.
I'm trying to get the RAV to get on the glass, and the glass would not work with me.
Mm.
So it just ended up a mess.
I think that's just a proximity issue. It's the anode's powerful enough to find the cathode without having to go through the glass, so that's what it's going to do.
But you saw me massage glass to where I can get it saturated, so I can
Yeah.
do it. It's not getting saturated, and there's reasons, but oh, this one is one of my favorites, I think, because I'd love your opinion on this one. Is this the one where it breaks off into yellow? Oh, okay. So watch the bottom blue, how it just sort of sucks into nothing.
Dude, that was so awesome. Hold on. I love
There's
that
no,
part.
Sorry, I'm watching it on my big screen, which is delayed. Oh yeah, I've seen that happen before, by the way, and it is super strange.
this is again. There's no. It's just a pan. There's no wire, cathode wire. The cathode is that water. But it's just strange to me how the plasma breaks in half and the cathode disappears.
How full of water is that tube?
It's not really. It's
Millimeter.
just at the bottom.
Or no water in the tube, only water outside the tube.
It's a millimeter water inside the tube. It's
Okay, yeah, I see it. All right.
yeah.
Yeah, I love it.
I feel like it's got to be It's weird because it's like resistance. There's still like a huge cathodic potential that's actually in this that push pull state, right?
Right.
So, but it's unable to exchange at the rate that it would be because of the offset bias, right? Well, there you go. So it was like there was still some monadic energy left for it to take in, but it was taking it in slower. That's
Yeah.
something like that. I don't know. It's very cool.
I sent another one where the cathode turns into a hydrogen flame and it just orange. And there's like a battle. The cathode flame does not want to go away. And I sent it to you, Nathan. I think it might be that one. So this one's has such an electrolysis that it kind of look at that, it's kind of a little hydrogen flame down there. The RAV still is cruising up there happy, but boom,
Mm,
we still get that. That's what I wanted to share. That one's interesting to me.
that is interesting because that's not how things don't do that, Sean. That's what they say, right? You ever see hydrogen? You ever see hydrogen go? You know what hydrogen would do? Is bust
Oh,
right out the top of that tube.
right, but you can see the electrolysis. So you see that it's high voltage electrolysis, and if you watch the bubbles, they put out the they're almost like snuffing out the flame, and they get more rapid, and then the bubbles calm down after it's gone. I don't know.
There's something. There's something to that. That's interesting.
It's bizarre, but interesting.
Because it's that, like I said, burning hydrogen just doesn't do that. Like you can't hold that back. You
I
know,
mean, yeah, AI spits that out when I put in the data, so I don't know what it is if it's not.
oh, I'm not saying it's not flame. That certainly looks like flame. It's got characteristics of flame.
And you know
Um,
that's catalysis. The water's not hot, by the way. Believe it or not.
Yeah, it looks like it's boiling. I'll be honest
No,
with you.
it's not. Yeah, it's
well,
not.
that's electrolysis, though. That's
Electrolysis.
hydrogen production.
It's
Oh,
splitting the
okay.
molecules.
Cathodic hydrogen production. Micro burst events at the surface.
Every one of those bubbles is flammable.
Yeah,
Oh,
but
you
why
know
is it
what?
contained? Why is it contained? It's
Why is,
not organized. Why is it contained?
This
why is
is
it
Stan
being going
Myers.
into the water?
This guys, this is what Stan Myers. Just think about it. You have a cylinder, okay, and usually there's a piston in there, and then now you're doing direct hydrogen inside the cylinder where the flame is present. The only difference is the piston would go up and down and cause compression at that point in time, and you would have a massive release of energy. You're seeing it in a different way here, in a more controlled environment. But this is Stan Myers.
That's interesting.
Yeah, but the thing about the compression isn't compression in this case. It's the decompression, and the fact that it's not decompressing. It's literally retarded.
Well, if it was, if
It's
it,
like retarded compression.
but if there was a piston in the top of it, and it would just fly out, you got a tremendous amount of pressure in there.
Yeah, but the thing is, Nathan, with no piston in, and I don't disagree with it if it was capped or if there was a piston in it, but at the same exact time, with nothing resisting holding it back, it there's nothing that should not be staying in the cylinder.
No, I understand, but what I'm saying is because you're pulling in air into the cylinder itself, okay, it's going to cause this reaction. That's why when it's open, it acts this way. But when it's closed, you still are going to get a tremendous amount of airflow in there. It'll suck in there right through the valve. So it'll still react this way. Dude, he would have a ton of compression in there in an instantaneous reaction. This is in slow mo compared to what he was getting.
Sean,
Yeah.
run the same experiment. All right,
Huh.
but just make something very very simple. Okay, like a pin or a piece of wire. Okay, attached to something ever so slightly smaller diameter than your tube. You don't want to make a bomb. Okay, and just attach it to the top of the cylinder with a spring and a stop. That way it acts like a valve. Okay.
At
And
the
see,
top?
yeah. Do
Okay.
you see what I mean? So you have something that's able to, articulate up and down based on the change of the pressure. So, if,
Yeah.
right. So if it's combusting, it should go up. And once that's down, then it should suck down. And if you have a small gap or you put a valve or something, you don't have to put a valve. It doesn't have to be complicated. You just need to be able to capture most, not all of the pressure differential. You're not looking for pure, sealed piston combustion.
Yeah. I can definitely try that. In one way though, I sent this. You guys showed this video last Friday where the plasma pulls the water inside the tube.
Mm-hmm.
Yep.
If I were to put a cap on this, I probably will see the same thing. The water will be pulled into the tube if I put a cap on that. Now, it's worth testing, but that would be a guess of mine.
Okay, Sean, look up
Mhm.
Stirling motor.
I've
What
heard of
it
it.
is, because I think that's if you started a RAV on the other side of the Stirling motor, it's basically kind of like a steam motor.
Yeah,
They
it runs
sell
on
little.
heat. Mhm.
They hold on. I have a picture. They sell little kits for it.
Yes.
So
Yeah,
here,
it's a heat water. I've seen them before.
I think this goes with that. So let me just
Oh, interesting.
I don't know if everybody can see it on the right hand side over here. Let's see if we can.
Mm-hmm.
Oh, that's a nice one too. It's
Yeah,
a one.
I've had something like that before. It's like a mini steam engine.
Yeah, so
And it's
you see the
sparkling.
connection, right?
Yeah, I do.
It has to do with pressure. It has to do with what's in the chamber, what's causing what's going on,
Yeah, exactly.
and we're talking about the RAV in the same uh, understanding right now. I think the two tie in. It would be an interesting concept to try.
I think
It
you're
would
right.
be because it proved the electric car like whole like how they debunk it and or try to debunk it and stuff. If you could show that with the RAV, instantaneously it's back in play.
Sounds like a
Yeah.
fun experiment. I needed an excuse to buy one, so thank you. I'm looking
Very
for the
cool.
one where we did the water RAV, Nathan.
Okay, okay. Sorry, I'll bring that back up. Sorry if my microphone's low, guys. I'll figure that out. I must have hit something before.
Yeah.
Okay,
Sorry.
Aaron
we-
says a rotary Sterling is faster. Well, a
Oh,
rotary Sterling also might play more to the character, the natural characteristics of the rotational nature of these processes, right?
oh,
So
thank
that
you.
might be interesting too.
Yeah, thanks for the tip.
I didn't know those were a
okay.
thing, but I think that's great.
I'm looking too, Nathan, just in case you can't find it.
What are we looking for again? I'm sorry, I couldn't hear you.
When I made the RAV inside water, water on top, water on bottom, and the RAV appeared inside the tube,
Yes.
completely submerged.
Um,
It's one of my biggest
that's not it.
accomplishments, but yet I can't find it.
It was a little while back. Hold on. It's at an angle.
Yeah.
I think that's it.
Is that one's the one that draws in the water? That's a cool
Yeah.
one though. See how it pulls it in?
Mm-hmm.
That's what I think if I put a cap on it, it would just suck all the water in. That's my theory.
Yeah, I'm there with you.
And it's that weird color that AI says is minute traces of hydrogen, ionized and then burned. But ionized it would be a different color. I don't know why AI says it's hydrogen.
Hmm.
Oh, Google doesn't know. Type from a hole in the ground.
I mean, that almost looks like that yellow of like a sodium lamp, to be honest with
Doesn't it? Yeah, it does exactly. Or
you. The only
even
difference is that sodium lamps put out so much. Oh, well, there it is. Never mind. I was going to say they put out so much ambient light, and it's all that coherent color.
right.
So, but you're getting flashes of it too.
And it's just Lake Michigan tap water. There's no salt. All my
Yeah.
experiments are not fancy, just water from the sink.
Yeah, I mean,
So
obviously, there's anytime it's sink water, it's going to be trace elements in it, regardless.
Sure.
Um,
Oh, you got the sound. There's something soothing about these sounds.
I can't hear it. I just like the way it looks.
Your rocket's gonna.
Yeah. Do you know what frequency it's running at, Sean?
So it has a range because I haven't really focused on locking in, but it's always in that 95 kilohertz to 100 probably 150 kilohertz. It's always in that range, and it's more in the middle. I'm giving you the extremes, but it's usually 100 kilohertz, 102, 104. What's interesting is you can add water, like a few drops of water, and you change the frequency. So it's a variable frequency control, which is interesting.
Well, you can see it in the color of the plasma that you change the frequency.
Yeah, exactly. I don't know why I can't find it. I only have 6,000 photos. Sorry, guys.
You're good, Sean. Yeah, I sent you a message before about your the actual transformers that you use. You had 4 in there, and I think the unit I bought had 2,
Mhm.
and I think that's why your RAVs are so much cleaner. So it gives you 3 different frequencies in there versus the 1 or 2 that I'm getting.
Yeah, I'm seeing like 3 more prominent, but the power supplies we have, if you wanted to buy one that's used for this purpose, you'd spend $1,000 for a used one. So what we're using is really a noisy, you know, power supply. So without a Faraday cage, you use try to clean up the noise. It's really tough to really lock it in, and I just haven't had the energy or the desire to pull everything apart and put a Faraday cage down and get everything locked up yet. So, but it seems to be working in that 3 frequency range that you mentioned.
Yeah, that's what I mean. You have 4 flybacks in your unit. The unit I have, I think, has 2 flybacks,
Right, it
and
does.
it's making a difference in your RAV, in
Uh,
how it's structuring and how many layers that it has.
I agree
So
with that, by the way, and having the multiple frequencies be the building blocks of it, that it's that is the structuring. It's all the offsets between the frequencies
mhm.
that exist. So by working not off of a single frequency plus its interference, or 2 and its interference, you're the more you bring in, the more stable the pattern becomes.
That's what I'm
Generally,
seeing.
that
yeah,
makes
that's the way that I see it, at least.
it makes sense, but I mean, we at least for what my setup, I'm working with DC. The frequency comes from the resonance of the RAV. It or it comes like we just saw there. It comes from the frequency of the flickering because it's a pulsing. So you have and it's not even an AC; it's a pulse DC.
Mhm.
So I'm not sure about Nathan's flyback because my flybacks are putting out a dirty DC.
Yeah, but I
No,
mean, is it though always? Because it's like I've shown before. If you have that DC pulse, the question then becomes: is it right? Is it like transient riding on an AC sine wave at any point? And just the realization that you could have something going in DC and have it ultimately form an AC, an AC signal, and then still have the DC riding behind it. Well, what happens is then the DC ends up riding the AC. It's something that Nathan and I had discussed at length on several
well,
occasions.
I'll tell you what it is. You're getting a big displacement current between the 2.
Yes.
It because of the way you're using your Tesla coil, Joe, with the inside and the outside, it really does act like a AC. Okay,
Mhm.
in this situation, where the same way Sean's does, even though it's pulsed by DC, it acts like an AC because it has AC slosh in it. It goes back and forth, right? So that's kind of the thing you're doing with both of them. That's the relatable part. I mean, the setup to get there is both pulse DC to get to the next, to get to whatever you're getting.
Hmm.
And I think that's why you're seeing kind of the same operation going on in there. You're not seeing a one-sided displacement current. And that's what the AC was providing because of the double diodes. You get it on one side only, either the positive or negative side instead of both. We're getting it on both.
And
So,
these power supplies are precipitator electrostatic power supplies, so they have some circuitry and quality control that to keep it at least enough static DC so they can put it in these industrial precipitators. So, I mean, it's not like your typical flyback. One, because it's more made to have a static field, DC static field. Two, it has the current limiting circuit, which I believe is one of the key factors to having a very clean, a really nice RAV, because uh, it manages current in a way to keep it stable, whereas a flyback power supply won't.
right.
And
Yeah,
so those
absolutely
are the
right.
two things. There's like that's an ingredient that I noticed um, that is a huge benefit for RAVs.
Well, yeah, the closer you can regulate that frequency and get it cleaned up and get rid of any noise to it is
Hmm.
better. So some diodes need capacitors over it and such to clean that up.
Yeah, that's
So
right.
here, I just want to show this for everybody. We're kind of talking around something. So let me just show what we're talking about here. This right here is Sean's setup. And you can see the big box in there.
Under the hood, I got a V8, V4.
Yeah, you do.
Yeah, this video is a classic at this point. This was like RAV infancy when he took this.
Right. That's
Yeah, look at
right.
that. He's got the hottest four banger there is.
That's not just a flat four. That's a turbo flat four.
That's what I mean. The one I have has two, so I'm getting two layers that are good. I'm not getting a third out of it. I think
Mm,
that's why is because you have this here that's driving it a little better.
it sounds right. Sounds logical.
Yeah, that makes all the sense in the world to me. To be honest with you, it really does.
Yeah, so I'm gonna have to upgrade to get to Sean's level to start creating the things he does. I think it honestly, Sean, if they made this board with two more, it would be even better.
I'd buy it. This is like the biggest you can get without paying $5,000, $6,000 for a used one, because this 60,000 watt power supply, it's a beast. I use it for electrics. I use it for RAVs. I beat it up all day long and sideways, and it's brilliant. And what's interesting about this is that they tell you in the documentation, which is literally one hand typed page photocopied, but it tells you um, it runs the best when you have an arc. I've never heard of a power supply saying I run the best when there's arcs and sparks. Never. You always have to try to avoid them. But
Yeah.
this, if you arc and spark all day long, it'll love you. And so, kind of
Well,
keep that in mind.
go on.
Is
That's because it's preventing backflow at that point. Like
that makes
to a
sense?
certain extent.
Yeah, that makes a lot of sense. I didn't think about it that way. Yeah, totally.
Well, I think in this regulator circuit, it actually pulls that back in and reuses it through that big capacitor he's got on this thing.
Yeah,
Yeah,
that could be too.
I agree.
So you know what? I'm kind of curious about this. Now that I look at it some more, if you could just add more to it, because they're telling you where the drivers are. I'd have to look at the actual circuitry of it.
Yeah. Um, I tried doing 230s, like two of the ones that you have,
Mhm.
and I fried one. So That was the end of my testing.
Oh, wow.
But I mean, this one's $250, and it's worth way more than that. And the reason why nobody uses this because nobody thinks to use a precipitator power supply for plasma experiments. So it just sort of lays low under the radar. So they're not charging a lot of money for it. I really believe that. I think the Chinese just made this for precipitators
Yeah.
and we'll snatch it off the shelf and go, look at this, we got a $2,000 power supply. I
Well,
really
yeah.
believe.
Sorry.
By the way, too, Nathan, you can save, I think, $100 if you buy this without the box and put your own box around it. I think you
Really?
get 150, yeah, 160. If you just Google precipitator power supply boards, I got this from AliExpress. So these four bangers here, you're only going to find them on AliExpress for a decent price. I mean, it might be different on Amazon now. I bought my other ones from Amazon, but
Okay. Now I'm gonna have to look because I can 3D print a box. That's not hard.
yeah, and you'll save over $100. So yeah, I mean, it needs cooling, so I mean, not a big deal. Put a fan, blows air across it, you're golden.
Hmm.
Yeah, and this, okay, so this is 60,000 volts. This, I've been hit by this about twice now in the most safest way you can be hit by it. And I still like shivers when I think about it.
Ooh.
So
It'll do that.
here's the thing. When you're running a big arc, let's say you want a 6-inch arc, what'll happen is it'll say forget you, and it will charge your whole desk with electrons. So when you go over to touch the box to turn it off, all those electrons on the desk, they go through you. So what I use now is I use a wooden spoon, an untreated wooden spoon handle, and I push all my buttons when I'm doing my plasma experiments because this thing is a beast. It's the safest for 60,000 volts, but it's not safe. That makes sense?
Hmm.
Yeah, it lights you up.
Hey, Joe, can you do me a favor real quick?
What you got?
Can you send me the video of you zapping that book? I wanted to show Sean how you use that Tesla coil.
Oh, I could zap the book again because I don't have a video of me zapping the book. I just zapped the book on the live.
Oh,
Yeah, but I can do that. Give me a second.
I saw it.
make sure you
No, I
turn the
saw
lights down. I want Sean to see the good effect of it.
it. Yeah, sounds good.
And Sean, he did this cool thing. It's like gold leaf or something on the book.
Yeah.
So remember the Tesla coil that you made us all zap ourselves with?
The one we re-engineered from the Chinese fascial face?
Yes, that's the one. So
I have a couple of books I could actually do.
Joe stuffed a big rod into it, and then now he's zapping things. I thought you'd get a kick out of it.
Well, that's not the only thing that I did. I just did that to pass some time while you went on again.
Oh, it's so cool looking though, because of all the placements of the foil on there.
Oh, wow. Yeah.
All right, here we go. We're gonna put Joe on big screen here.
Also, Nathan, if you put a tight spring at the end of your boards, you'll get different frequencies when the spring bends.
Oh, really?
Yeah, I just learned that today. All right. He's got a lightsaber with a brass tip.
I told you he stuffed a huge rod in there, man.
Oh, whoa. That is crazy. Oh, it's trying to communicate.
It's so awesome looking.
That is fascinating. Yeah. Are you getting bit by the electricity?
No, not yet. Wait until it saturates the book,
Yeah, yeah,
because it does.
yeah, exactly.
All right,
Cool.
I have another one with gold leaf that it's right here. Hang on.
Is it
Here we
gonna
are.
damage it?
Hold
We're
on.
zapping the books instead
This
of
is an
reading them.
Aleister Crowley book. Yo, look at all the gold on this one.
Oh my
Oh,
goodness.
here we
Oh,
go.
it's Satanic Bible. Oh, it
It's
should
not
be.
the Satanic Bible.
It should be zapped.
Ah, fuck.
Oh, yeah, I gotcha. Look at that.
Wow. Wow. Yeah.
Well, let's see if I can get it in the dark. It's reflecting too much. Hold on. Ah.
Is it making a noise?
Oh yeah.
Yeah, Joe sure is.
It's it's traveling to every design piece.
Oh, yeah, there it is. Oh, that
That's
was a
what I'm
good
trying
one.
to show you. I got to do it
Yeah.
like this. That's why I'm coming from the wrong side.
Is it talking? It sounded like that Lost in Space robot. Yeah, the demon symbols seem to get the brightest.
Yeah, it's not the demon symbol, but yeah.
It's like,
He's got the skull to light up over there. Look at that.
I know. It's all way in the back.
Oh, hit the lettering on the top, Joe. That one was the best.
Yeah.
Oh, yo, let's hit the Kabbalah. Let's hit the Kabbalah right there.
Oh wow, look at the lettering. Oh wow.
I'm hitting Keter.
It's really cool looking. I mean, it just makes the book look cool.
Hold on. Now, this is what I've been refraining from doing. See what that is?
Oh,
Yeah.
it's got the side there.
Oh, that's right.
Oh, look at that.
What? That is cool. Oh, I'm trying that.
Oh, fuck.
I was
Yo,
waiting.
that looks so crazy. It's not even showing it good.
Yeah, I imagine, but it looks cool on screen.
Oh, man.
See. I can't find my RAV in a glass, sorry. Lab and water. I mean my water RAV.
What else I have to that?
It's all good. We get to see Joe zap himself a little bit. That was
Yeah, that
awesome.
was worth it. Plasmoid infused occultic book collection. That's what Sears Vortex says. That's
Yeah.
funny. That's
Oh, I
funny.
love it.
I'm just getting to the comments. I'm sort of gonna expire here, guys. Forgive me about the video. It's my computer.
This whole book might go because this is like a copper looking book. I don't know.
You're gonna get whacked hard. I love it. He's gonna get whacked hard.
Oh,
Unless-
that was a good one. Look at the K. Oh, the
Wow.
colors.
Yeah,
Tesla.
it looks like CGI.
Oh, he made the lightning work.
Oh no way!
That's a cool effect, Joe. That's awesome.
You got to get a photo of that. I'm reading my book, and hide the testicle out of the picture.
Oh, here we go.
The back. Oh wow! You can just see the metallic that they put in the ink. Very cool. So what'd you do last night? I watched my friend shock his books.
I'm charging them up.
He didn't read it or anything. He just shocked it.
I've read them all.
I might buy some more books now.
That's right. Stock them so I can get the info inside.
Apparently, almost all the books I have some kind of metallic on them.
Oh, that's cool. That one was really good. Oh, look at that.
I wonder if all your Dungeons and Dragons book do that.
Oh. You know what? Can you imagine just hooking a couple wires up strategically to this thing? It would make
That's
it a
really
whole different
cool.
book.
Yo, Nathan, you see this?
Oh, dude, I'm seeing it. Yeah.
Yeah. taking knowledge to its highest state. That's funny, Aaron. Too funny. A cymatic power pattern. Interesting.
Look at the colors in that, though.
Yeah, they sell those metallic books at bookstores for discount because people don't want to think and read hard books.
Oh, fuck. That was a good one. That was like a full
Oh,
grab,
love it.
yo.
I bet the rod makes the shocks worse. I really do.
Oh, yeah, it was hard.
Especially that
Oh,
rod like can
Oh.
do the number.
Let's see.
he's got another one.
I have so many. I'm telling you, this
Is
one's
that-
not as good. The gold ink is not that strong on this one.
Is this Marcus Aurelius?
Yeah, that's Marcus Aurelius.
Oh, I have his book. Oh, he's a brilliant guy.
Oh yeah.
Oh, man.
Well,
It's like worth the price of admission here. I'll tell you that.
yeah, for my expense. God damn it. All right, let's see.
Well, I appreciate you guys having me on. It means a lot, and thank you for answering my questions. I need to run.
Well, Sean, it's been real. I miss you, brother. I hope you feel well and be in touch, man.
Thank you so much, Nathan. Still there, buddy?
Thank you, Sean. Appreciate everything, man. Hey, we're gonna have to have you back on when you get those Tesla coils.
Oh yeah, I can't wait. Will do. All right, guys. Have a good night. Much love.
Good
Have a great night, Sean. Oh man.
All right, hold on.
You got another one?
Oh, dude, I told you I had so many. Yo, look at these patterns because it's all sacred geometry.
Oh, look at that. Okay.
Oh, yo, here's the one right there. It's not getting it that good. If I could get that whole thing to charge up, that's the energy grid that we're always seeking, isn't it?
Yeah, you know what? You're gonna have to just do these on, you know what I mean? Like videotape it from a distance, and we'll zoom it in and stuff. Make shorts out of it. It'd be awesome.
Yep. I'll check it out. I mean, it's a little silly, but at the same time, it's pretty cool.
Oh, dude, that's just fun.
And especially when I hit myself, I know everybody's got to get a good kick out of that.
I know I did. That was awesome. Oh, here we go.
The books just keep on coming, dude.
Dude, it's got like every sacred symbol in the world.
You know what? Try to turn it down a little bit. Sometimes turning it down is actually the thing to do.
There you go. That looks good. Oh, hold on. You hit the side and the front lit up a little bit.
Really?
Yeah, see that again. No, maybe it's just me.
I don't know, bro. The books just keep on coming and coming, and they all like seemingly have gold leaf. So I think I'm done for now.
Oh man, that thing's
Oh wait,
addicting.
hold on, one more thing. Look, I have
Yeah,
this
one
beer
more.
label.
Okay, here we go.
I have a beer label, but look at this.
Ooh, you're getting zapped.
Oh
You're
yeah,
so getting zapped.
if I roll that up, it's a capacitor. Freaking Mylar is what it is. Oh, this is such a bad idea. Hold on, let's see if it. All right, it's not moving, so that's good. Oh, yo, it lights up the book underneath it.
That's cool. Oh yeah, that's awesome.
Oh yeah. Yo, what? Check this out. It's not doing it. Oh, there it is. It's this one. It's lighting up the bottom of the book. I don't know.
That's so awesome, man.
All right, I'm done now.
Oh, it's funny. I think Sean got us those to torture us and have a good laugh, and we're putting them to good use.
It's, you know what? I play with that thing all the time.
It's so great. Yeah, we no longer read the books. We just make sure they have foil on them and zap them. Oh, that's so awesome. I'm going to have to try that with everything now. I think I'm going to get me some gold books just to try it.
Then I had a duck. Yeah, man. Well, honestly, you know what the probably more interesting thing to do is to create like geometric, sacred geometry, lattice, grid patterns, and then run the high voltage through them. Like a circuit. You know? Just saying.
Oh,
I'm not saying anything crazy is going to happen, but I will say that, you know, it could actually have, you know, electromagnetic effect.
well, yeah, just put the one wire energy to it and we'll see if it sparkles. You know what I mean? That should light it up pretty good, actually.
Oh, yeah.
New use for a book, huh?
Well, I charged them all up. Now,
Now you get zapped
it's all
later.
gonna come true.
Just gonna run around in socks later and get zapped by his books. That's gonna be great. You just add that little bit of energy that it needed to get over the top.
Yeah.
No, but that lightning though on that Tesla one, man, was awesome. Like it because it went to the circle, so you could see the
It
lightning
did.
come up.
That was actually the best one because it was like meant to be. It was literally like meant to be. I could guarantee you nobody's ever done that before with that.
Oh,
book.
but you know
Or
what?
probably with the book in general.
If you put a little splitter like a coat hanger on the top, you can get both sides at once, and then it would look. You know what I mean?
Mhm.
That would be awesome.
Yeah. Dead fish is like, am I conjuring demons? I mean, I don't know. Maybe when I hit the Crowley book, maybe. You never know.
No, he didn't see
Yeah.
any spirits come out of him. That's for
No.
sure.
Do I still have
dark
all
entities.
my fingers? The Philadelphia experiment. Yeah, I left all but my middle finger. You know, I left all but my middle finger in the Kabbalion, you know?
Yeah, those things bite a little bit. A little shock in there.
Oh yeah, it doesn't hurt too bad, but I'll tell you what, even if knowing that it could be coming at any time, it's still surprising no matter what.
Yeah. So great. Oh man, that's so awesome, Joe. All right, man. It's been about 2 hours today, guys. We're about done, man. We zapped everything and looked at a bunch of cool stuff, and Sean hung out with us, man. It's been an awesome night, brother.
Yeah, man, no, it's good, man. It's really nice to have Sean on, you know, when he's feeling up to it and see what he's up to. And that's the great thing about it is, you know, rather than just me and you talk about it and sit there and speculate and scratch our heads and wonder all the fine points, you know, the man himself is there to tell you exactly what is or isn't. So cool. But I
Yeah.
think that if there's a big takeaway from today's episode, you know, it's two things, you know. The first thing that we talked about being the those three lights at the bottom
Yeah,
of that tube.
we'll check that out.
I think that that's significant, you know, and I think that the other thing is just the curiosity of that hydrogen reaction because things don't do that.
Nope.
Yeah, no, like if you light hydrogen and it combusts and it's in a tube, it goes out the top, you know. And honestly, sometimes even if it's contained, even if it's open top, if there's enough of it, it'll still create enough compression and expansion to blow the tube up into pieces because it's just expanding that fast. So
So
there's
think,
nothing that should have kept it in that tube.
let's just think about it this way. If you make a spark plug which is designed to spark, but you initialize it like it's a RAV, then you have a RAV in the chamber with that. It gives you the exact reaction you're looking for.
I don't disagree. And when you brought up the steam motor, and then Aaron said about the rotary steam motor, which I'm sure it probably is a thing. I just wasn't aware of it, honestly. Yeah, adding the rotation into it,
Mm-hmm.
very, very smart thing to do. So if Sean was actually gonna, maybe try that out, I would definitely suggest looking into the mechanical one. Yeah.
Dude, one of those things is cheap enough.
He made it up.
I mean, nice
Well,
just
guess
to run
what?
it.
You know what? That doesn't mean it can't be done. I mean, there's realistically rotary engines work just like a piston does. It's just in a different configuration. So there's no reason that it couldn't exist. But whether or not it does, I guess since you made it up, I don't know.
Well, I'm going to tell you right now, Stan Meyer's enthusiast said they seen what Sean's doing there and understood what he was doing. I think they'd be very excited to make spark plugs that look like that and create RAVs inside of them. It may be an answer to, kind of what he was doing, breaking it down immediately, because that water was not under pressure yet.
No.
And it was having that reaction. I want to see how much more pressure with some bigger reaction is.
Right. So with Stan Myers now, that actually raises the question of and this is where we're weird compared to most people. See, most people have an idea and they figure out the means to their end and work on it, and then once that is achieved, that's good enough. You know what I mean? Like what that does though is sometimes blindside you to the implications of maybe what it is you're finding, right? Someone like Stan Meyer's case, he could well have been using the RAV exactly as we describe it all along, but unknowingly and unwittingly to the overall implications, just simply because it works so well in his configuration. I don't know that that's the case, but frankly, I think that it holds a lot of water. Holds a lot of water.
No, I 100% agree with that. And you consider the way they build engines today, there's one of these on top of every single one of them. There's like basically a flyback on top of every one of these cylinder chambers. It wouldn't be unheard of. That they knew exactly what they're doing and presetting the cathode and then running it and then bam. I mean, yeah, I think it's all coming in line right there. We're gonna have to do some more experiments on
how a traditional spark plug works, it's only sparking one way. It's giving an anode just simply a place to go. So what happens when you put pressure up the other end? What happens when you put pressure on the other end? I mean, usually they use pretty high temperature materials like tungsten and things like that. I forget, they use one other very specific thing. But now, I mean, if you could actually get that to nucleate, right? Like then or just frankly put a medium in between it too. You could do that. Whatever the case is, I mean, there's no reason why an actual spark plug wouldn't work as.
No, I'm there with you.
For RAV generation. Yeah, Iridium, thank you, Deadfish. Much appreciated. That is exactly what I was.
Well, things we're going to have to look into in the future. So, anyway, I want to give a shout out real quick to Gutters Pub. I want to say thank you for getting an Old Man Builds membership. And then I'll be on Traveling Fools later, man, hanging out. So I want to thank everybody for hanging out with us today. Thanks, Sean. Thank Joe for coming in. Guys, it's been an awesome night, man. I really appreciate it. And thank you, Joe, for pulling out the books and doing all that, man. It was awesome.
Yeah, I'll take the shot for you any day, brother.
Don't worry, I'll zap myself here in a couple of days. I plan on getting my lab up and running and doing live. So I'm gonna get plenty of shocks myself.
Awesome.
Right on, guys. Have a great night.
Peace and love.
The old man Bill. The old man Bill. The old man Bill. The old man builds. The old man builds is broken in the head. People not seeing reality has put him in the red. Where conscious and spirituality been stricken from the norm and replaced with the ignorance of basic magnetic form. The geometry of God keeps running through his head. That's what makes old man builds broken in the head. The old man builds. The old man builds. Spheres of destiny are spinning in his mind, making him travel back and forth in time, battling the establishment for just a little recognition. Has him forcing the world to understand his premonition. That world will have all the technology in the end, even if it means his life will fail to extend. The old man builds. The old man builds. The old man builds. The old man builds. Fears of destiny are spinning in his mind, making him travel back and forth in time, battling the establishment for just a little recognition. Has him forcing the world to understand his premonition. That world will have all the technology in the end, even if it means his life will fail to extend. The old man builds. The old man builds. The old man builds. The old man builds. Fears of destiny are spinning in his mind, making him travel back and forth in time, battling the establishment for just a little recognition. Has him forcing the world to understand his premonition. That world will have all the technology in the end, even if it means his life will fail to extend. The old man builds.